Welcome to INSITECT. Today we are talking about the critical architecture and standards underpinning modern fire alarm systems. This is a deep dive that moves far beyond the simple concept of a smoke detector and a loud buzzer. We're really looking at these installations as highly complex, integrated technological networks.
That's absolutely right. I mean, when people visualize a fire alarm, they see that one basic component, a detector, maybe a pull station. But what we've compiled and what we're analyzing here, it treats these systems as essential, critical, integrated safety networks. They are, you could say, the core intelligence layer of a building's entire emergency response system.
Right. And our mission today is to be your expert guides through these layers of technical specifications and really rigid code requirements.
Yeah.
We want to help us all understand what turns a collection of sensors into a true life safety network. We want to grasp the sheer operational and architectural sophistication required to protect people today, all based on these stringent standards like NFPA 72.
And if we just start with the fundamental definition, a fire alarm system is a dedicated safety network that performs two main functions: detection, which is usually smoke or heat, and then the activation of alerts. This happens through a coordinated sequence involving the sensors and a centralized control panel. But the critical question we have to address is the why.
The why, exactly.
Why has modern safety moved past those simple, self-contained units and now demands this extraordinary level of sophistication and networking?
I think the immediate implication, and this is really the hook for our whole discussion, is that modern systems don't just alert you. They don't just make a noise. They orchestrate a complex, coordinated response across the entire building. The moment an alarm is confirmed, we are talking about integrated building systems coming online automatically. This includes coordinating things like HVAC shutdown to stop smoke from spreading
through the ventilation.
and the crucial elevator recall sequence, sending cars to a safe floor so emergency responders can actually use them.
And that functional integration is the key takeaway right from the start. Physical safety is now it's inextricably linked to building intelligence. The system isn't an island. It's an integrated platform that has to communicate flawlessly with the building automation platform, the BMS, and all the other infrastructure.
So if that fire alarm system fails to transmit the necessary signal, maybe because of a fault, power loss, or even a data collision, those vital smoke control sequences just don't happen.
And the building's risk profile changes instantly. It just emphasizes why the system's performance relies entirely on meticulous design and, just as importantly, unwavering maintenance throughout its entire operational life.
Okay, so let's unpack that core architecture layer by layer. Our sources consistently define the fire alarm system as this coordinated network, and it's built on three functional layers that have to work together. You've got the sensors, the control panels, and the notification devices, and they're all constantly monitoring the environment for signs of fire and processing that data immediately.
Exactly. So while the sensor layer is providing the input, the control panel's role is really the central processing unit. It's the decision maker for the building's safety response. It's so much more than a simple switchboard. When it gets a signal from a sensor, let's say a slight obscuration reading from a photoelectric chamber, the panel evaluates that signal against these complex, pre-programmed thresholds and logic sequences before it decides to activate anything.
So it's running a constant real-time risk assessment.
It is, based on its internal logic, which is just crucial for telling the difference between a minor event like some steam from a shower and a genuine fire threat.
This sophistication leads directly into the advanced features that distinguish a modern system from an old, conventional one. Our sources repeatedly highlight things like addressable loops and cross-zone detection. Addressable loops are pretty much the industry standard now in commercial facilities. Why is that specific device-level identification so vital?
It just fundamentally changes the speed of intervention and the maintainability of the system. I mean, imagine a conventional zone-based system in a huge warehouse, say 100,000 square feet. It reports Zone 3 fire.
Okay, so where's that?
Exactly. Emergency responders or the facility staff now have to search maybe 20,000 square feet to find the source. Contrast that with an addressable system that reports smoke detector 14A, located in the West Utility Corridor, is in alarm.
That's a huge difference.
It's the difference between minutes and seconds of response time, and that's critical for containing a fire.
And what about that other concept, cross-zone detection verification? That sounds like it's specifically designed to fight the nuisance alarm problem.
It is. It's a high reliability requirement, and it's designed to prevent unnecessary shutdowns or evacuations in mission-critical places. Think data centers, hospitals, specialized manufacturing plants. The system logic actually mandates confirmation from multiple input devices, often sensors in physically separate zones, or even requiring signals from sensors using different technologies like smoke and heat before it escalates to a full alarm.
Which just gives you much higher confidence in the activation.
Absolutely. It prevents a single false trigger from steam or dust from shutting down an essential operation for no reason.
Okay, now let's move to the physical elements the building occupants actually see and hear, the notification appliances. This is where the abstract code requirements of NFPA 72 directly intersect with physical safety.
And the requirements here are incredibly precise. They're all evidence-based. Let's start with the audible alerts, the horns. They have to produce sound levels that exceed the average ambient noise level in a space by at least 15 dBs.
That ensures it's startling, unmistakable.
Right, even over normal background noise.
But the requirements get even more specific when you get into sleeping areas. It's not just about loudness there, is it?
No, it's about efficacy. In sleeping areas, the standard is very strict, 75 dBA minimum at the pillow. But NFPA 72 also made a crucial research-driven mandate about the frequency. They require low-frequency 520 Hz square wave sounders in those sleeping areas.
And why that specific frequency?
The reason is simple but profound. Numerous studies showed that lower frequency signals are just significantly more effective at waking people up, especially children and individuals with age-related hearing loss, compared to those traditional high-frequency piercing tones.
That's a perfect example of how the codes evolved based on applied science.
It is. It's an engineering-based response to a clear safety vulnerability.
Okay, moving on to the visual alerts, the strobe lights. These are mandatory under the ADA, the Americans with Disabilities Act, to ensure accessibility for hearing-impaired occupants in public spaces. And here, the engineering focuses not just on output, but on coordination.
The need for coordination is non-negotiable. It's governed by UL 1971. If multiple strobes are visible in the same field of view, they absolutely must synchronize their flashes.
Why is that so important?
Because if they flashed asynchronously, even by milliseconds, they can create this disorienting, rapid flicker effect that can actually trigger seizures in photosensitive individuals. So the system has to prevent this from happening, ensuring the devices remain a safety mechanism and don't become a hazard themselves.
And the light intensity, the candela selection, that also requires precise engineering, right? It's not one size fits all.
Not at all. The candela, or CD rating, defines the intensity of the light, and it can range from 15 CDs up to 185 CDs or even higher. The selection isn't arbitrary. It has to be precisely matched to the room dimensions, the ceiling height, all based on specific tables within NFPA 72.
So a small office might get a 15 CD, but a big assembly hall needs something much stronger.
Exactly. You might need a 75 or 110 CD device in a larger space. Engineers have to calculate the required intensity to make sure the entire area gets the minimum required light coverage. It's a precise application of light science.
Then the final and maybe most complex element of notification is the voice systems, the Emergency Voice Alarm Communication Systems, or EVACS. This goes beyond simple tones to deliver actual instructions.
And the scientific standard that governs the clarity of those messages is the Speech Transmission Index, or STI. EVCS design requires field testing to ensure a minimum 0.50 STI score for any life safety messaging. The STI score is basically a number that quantifies the quality and clarity of the speech, the intelligibility.
So if the score is too low, the message is just garbled.
Muffled, garbled, washed out by the room's acoustics. Imagine a highly reverberant space like a gymnasium or a concrete stairwell. If that distorts the sound, the system fails.
Because a message that can't be understood is useless.
Precisely. Achieving that 0.50 minimum forces engineers to really account for speaker placement, output levels, and even the natural acoustic properties of the room itself. It often requires acoustic modeling in the design phase.
Let's shift back to the central brain of the system. We need to talk about how this complex network communicates with the rest of the building's infrastructure. This integration is so vital.
It has to be seamless. This integration enables those crucial life safety smoke control sequences we mentioned. For example, detection in a machine room has to trigger an immediate HVAC shutdown in that area. Detection in an elevator shaft must activate elevator recall.
And this all relies on sophisticated data exchange. I've seen these systems leverage protocols like BANet and Modbus, which are open standards, but they also use proprietary protocols. What's the trade-off there?
Well, open protocols like BANet and Modbus are fantastic for achieving unified building management. They allow the fire panel to communicate with chillers, air handlers, lighting controls, all through a single interface. They maximize interoperability.
But proprietary protocols must have some advantage, or they wouldn't exist.
They do. Sometimes they're necessary within the fire alarm network itself because they can be optimized by the manufacturer for speed, for signal integrity, for high throughput, all things that are critical when milliseconds matter. So the trade-off is often between highly optimized performance within one ecosystem versus maximum compatibility across all the different equipment in a building.
Let's dedicate some serious time to the sensors. I mean, if the control panel is the brain, the detection technologies are the sensory nervous system. If the sensor is poorly selected, or it fails, the brain gets no signal and the whole network is useless.
Absolutely. The technology choice dictates the safety performance based on what kind of fire you expect. Is it fast flaming, slow smoldering, high heat? And what are the potential sources of nuisance alarms?
Let's start with the industry workhorse. Smoke detection, specifically the photoelectric units. Can you walk us through the physics of how they work?
Sure. Photoelectric detectors operate on a simple but effective principle: light scattering. Inside the sensor chamber, you have an infrared light source and a photosensitive receiver, and they're positioned at an angle so the receiver doesn't normally see the light beam.
It's just sitting there in the dark.
Right. But when smoke particles, which are typically larger and more visible, like from a smoldering fire, enter the chamber, they scatter that light beam, deflecting it onto the receiver. Once enough light hits that receiver, the sensor triggers a signal to the panel. Because they rely on these visible particles, they're exceptionally good at detecting the early stages of slow, smoldering fires.
So if they're the workhorses, what ensures they stay reliable over time? They must get dirty.
They do, and that brings us back to those crucial standards governed by UL 268, which mandates something called drift compensation.
Drift compensation.
It's arguably the most essential operational security feature of a modern sensor. Think of the chamber like an odometer that slowly accumulates dust. That contamination gradually changes how light behaves in the chamber, making the sensor either too sensitive or worse, dangerously desensitized. Drift compensation algorithms continuously track the normal, clean baseline reading. As the chamber slowly gets dirty, the algorithm automatically adjusts the sensitivity threshold to keep the detector operating reliably.
So it's constantly self-calibrating. That's fascinating. But what happens when it gets too dirty to compensate?
When the contamination reaches a preset limit, the algorithm sends a distinct trouble or maintenance required signal to the control panel. That requires someone to physically clean or replace it.
So that maintains reliability and cuts down on false alarms from a dirty sensor.
Exactly.
Okay, that handles contamination on a normal level, but we have to confront the high ceiling problem. This is where I get a little skeptical about standard ceiling-mounted sensors. In these huge spaces, warehouses, atriums, theaters, anything above, say, 30 feet hot smoke rises. But then it cools and stratifies. It just hangs there and never reaches the detector.
And that stratification is a critical failure point. You cannot rely on the standard 30-foot radial coverage rule in those scenarios. It just doesn't work. This phenomenon requires specific, specialized approaches. The solutions often involve projected beam units, which we can get to, or stratified sampling.
Stratified sampling.
It means deploying detectors or active sampling ports at multiple elevations, like mid-wall, to catch the smoke plume before it dissipates at the ceiling. Fire safety engineering has to be contextual. The standard spot detector just can't meet the safety needs of a high bay environment.
Okay, let's pivot to environments where smoke detection, even with all this tech, is just a bad idea. Think industrial kitchens, boiler rooms, parking garages.
Right, the nuisance environments. This is the domain of heat and flame detection. Heat sensors are the necessary fallback for places where cooking aerosols or vehicle exhaust would constantly trigger smoke alarms. And we differentiate between two primary types, both governed by UL 521. First, you have fixed temperature detection.
That's a simple one. It just activates at a preset temperature, like 135 or 200 degrees Fahrenheit.
Exactly. Designed for a slow fire where the temperature will eventually hit that limit.
But for a faster fire, like a fuel spill, that might take too long.
It would, and that's where rate of rise detection comes in. These sensors trigger not on an absolute temperature, but on the speed of the temperature increase, typically if it jumps more than 12 to 15 degrees Fahrenheit per minute.
So it's looking for a sudden, aggressive fire.
Yes, but there is a critical limitation here: thermal lag. The sensor's element takes time to heat up and match the ambient temperature. In a very dusty environment, or if the heat source is far away, this lag can affect performance.
Now let's move to specialized high-hazard areas. Petrochemical plants, paint storage. This is where we see flame sensors, which are looking for electromagnetic radiation, not the physical byproducts of a fire.
Flame detectors are extraordinarily fast. They use specialized sensors to look for specific wavelengths of light. UV sensors detect the ultraviolet radiation from burning hydrocarbons, while infrared sensors target specific wavelengths, often the CO2 emission signature.
And in modern high-reliability applications, you often see them combined, right?
Yes, UVIR combination units. They require the presence of both specific wavelengths simultaneously for improved reliability, which drastically reduces false alarms.
But I imagine that speed comes with a trade-off. What can fool them?
The trade-off is susceptibility to non-fire energy sources. Welding, intense artificial lights, even direct sunlight can generate light in that same UV or IR spectrum, causing false alarms. This means you need a significant environmental safety analysis before you deploy them. Engineers have to confirm clear sight lines and make sure the device is carefully shielded from routine operational light sources.
This constant challenge of nuisance alarms seems to be the central headache. How do modern systems use technology to reduce that headache without sacrificing response time?
That brings us right to the current state of the art, advanced detection systems. The main goal here is to integrate multiple data points and add intelligence right at the sensor level.
The multi-sensor units are the best example of this. They combine optical and thermal elements, but they go even further.
They too. A multi-sensor unit might have a photoelectric chamber, a thermal element, and maybe even a CO sensor, all in one housing. The microprocessor inside doesn't just look for one signal. It analyzes CO levels, particle signatures, and temperature profiles all at once.
And that correlation process is what prevents the nuisance trips.
It's the core benefit. For example, if the sensor sees a high particle count, like smoke, but the temperature is stable and there's no increase in CO, the logic can confidently say, this is probably steam or dust, and avoid a full alarm.
For the absolute highest level of protection, think historical archives, clean rooms, data centers, we move to aspiration detection. Most people know it as VESDA.
VESDA is the pinnacle of early warning sensitivity. It works fundamentally differently. It doesn't wait for smoke to rise to the ceiling. It actively draws air samples from the space through a network of specialized pipes with tiny sampling holes.
So it's sniffing the air.
It's sniffing the air, and that air is routed to a centralized, highly sensitive, laser-based analyzer. Because it's analyzing the air sample directly, it can detect submicron combustion byproducts long before you'd ever see smoke or a spot detector would react.
And its critical use case is protecting assets, not just people.
Exactly. It's about critical asset protection. In a data center, the cost of downtime from fire damage or even from a fire suppression system discharge is way more than the cost of the VSDA system. It gives facility managers vital time to investigate and address an issue, often without a full shutdown. And it doesn't just have one alarm threshold, it has multiple stage thresholds.
Alert. Action. Fire 1. Fire 2. How does that translate into operational safety?
It defines a proactive response. The alert threshold might be set at an extremely low level, maybe 0.005% obscuration. That might just notify security. The action threshold escalates it. Only when you hit fire 2, say 0.8% obscuration, do you get a full disruptive evacuation response.
It allows for intervention before a crisis.
That's the whole point.
And finally, let's revisit the high ceiling problem with an architectural solution. Beam smoke detection.
Beam detection is for horizontal coverage over extreme distances, from 15 to 100 meters or more. A transmitter sends an IR beam to a receiver, and if a smoke plume obscures that light path by a certain percentage, it reports a fire.
And the practical benefit is huge. You don't need hundreds of spot detectors on a massive hangar ceiling.
Exactly. You install a handful of beam detectors. The key challenge, though, is alignment. Buildings settle, things move, and if that transmitter and receiver get knocked out of alignment, the system fails. So it requires regular, specialized maintenance.
Okay, moving from the science of detection to the resilience of the network itself, we're now shifting our focus to how the system maintains its integrity, basically the security view of the fire network.
And that divergence between conventional and addressable systems is maybe the most fundamental choice a designer makes. Conventional systems are simple. They group sensors into zones. A signal means a fire somewhere in that zone.
Addressable systems, the modern standard, give a unique address to every single device.
Every sensor, every horn, every module.
And as we discussed earlier, that's crucial for faster response. But how does that unique address help the maintenance crews?
Think about troubleshooting a fault. In a conventional system, you get a ground fault signal, you know it's in zone 5, but you have to physically search every wire and junction box in that area.
Which could take hours.
Or days. In an addressable system, the panel tells you, ground fault reported at device 10B14. The technician knows exactly where to go. That efficiency translates directly into less downtime and higher system availability.
Precision requires power, and fire alarm systems require continuous power, usually converting AC to a supervised 24 VDC supply. But the real security layer is the battery backup. What are the standards there?
The NFPA 72 requirements are demanding. Standard commercial buildings require 24 hours of standby power plus 5 minutes of full alarm operation. This ensures that even during a long power outage, the system stays fully supervised and ready.
And for high-rise buildings, it's even longer.
Significantly, sometimes jumping to 60 hours of standby, reflecting the greater complexity and time needed for a high-rise evacuation.
But here's the critical check that often fails in the real world. Batteries degrade. How do you ensure a battery that's been sitting for months can actually perform?
That's the whole purpose of mandatory regular load testing. A battery might show the right voltage on a meter, but if you don't load test it, meaning a simulated discharge under actual alarm conditions, you can't confirm its capacity. NFPA 72 requires periodic discharge testing to verify the battery bank can really meet the standby and alarm requirements.
Beyond power, the system architecture has to be fault-tolerant. This is about maintaining protection even when things break.
Fault-tolerant design is baked into the supervision requirements. Systems have to continuously monitor the wiring for opens, shorts, and ground faults. If a fault occurs, it immediately generates a trouble signal, alerting operators before an emergency.
A system that can't self-diagnose is a blind system.
Exactly, which could be compromised without anyone realizing it until it's too late.
Let's get into the physical security of the cabling, the network wiring, and pathway survivability. This is where you really separate the robust systems.
Absolutely. The distinction between wiring classes, specifically Class A and Class B, is fundamental.
Okay, so Class B is the basic one.
Class B uses single paths. If there's a break in the circuit, a wire gets cut, a fire damages a junction box, you lose communication to everything downstream from that break. It's a single point of failure.
And Class A?
Class A wiring provides redundancy through supervised return paths. The wiring leaves the panel and comes back to the panel. If a break occurs, the signal can still travel back to the panel through the alternate path, maintaining communication with all the devices.
That's a massive upgrade in survivability. But even that wiring can be damaged by fire. This brings us to the highest level of physical security: pathway survivability levels.
And Level 3 protection is the ultimate physical hardening of the network. It's mandatory for critical circuits that have to operate during a fire, like the communication lines between panels in a high-rise or the circuits controlling smoke evacuation fans. Level 3 requires the wiring pathway to maintain its integrity for up to 2 hours under fire conditions.
2 hours. How do you achieve that in practice?
Specialized installation techniques, often using mineral-insulated or MI cables, which are inherently fire-rated or dedicated 2-hour fire-rated raceways. It's applying a physical security layer directly to the communication network.
Shifting to external signaling, getting the alarm out of the building to the monitoring station. We've moved beyond old telephone circuits, the DDTs.
Redundancy in signaling is now mandatory. While DECTs still exist, they're often augmented or replaced by cellular communicators. The gold standard is a dual-path configuration, using both cellular and an IP connection simultaneously.
So if one path fails, the other takes over instantly.
Correct, and all signaling paths have to be continuously supervised. The monitoring center expects a periodic test signal, a heartbeat. If that heartbeat stops, they know there's a communication failure, even without a fire.
Let's talk interoperability again. How important are open standards like BACnet or Modbus for the facility managers who interact with the system every day?
They are crucial for unified building management. Open protocols let the fire panel integrate with a larger building automation platform. This lets facility managers use a single interface to view alarm history, system status, and troubleshoot faults across everything: HVAC, lighting, security, and fire systems.
And finally, the most crucial interface of all: the fire brigade interface. What do responders need to see when they arrive?
Local codes mandate standardized interfaces and displays, usually in a fire command center near the main entrance. These displays have to show the full current system status, the exact address of the device and alarm, the status of power supplies, any trouble signals. This data access is mandatory, and it's what their initial tactical decisions depend on.
And this interface brings us to the operational control layer, the firefighter's smoke control station, or FSCS. This gives them manual override.
The FSCS is a key life safety device. while the fire alarm system automatically initiates smoke control sequences. Activating fans, closing dampers. Firefighters, once on scene, must have the ability to manually override those sequences. The FSCS panels show the real-time status and allow them to take manual control of the HVAC systems to assist with tactical operations, like directing airflow to contain smoke.
Shifting gears completely, let's analyze the rigorous framework of compliance and the long-term operational challenges. The entire field is governed by these incredibly rigid standards.
It is. In North America, NFPA 72 is the Bible. It governs design, installation, testing, maintenance, everything.
And internationally.
You're mostly looking at the EN54 standards in Europe. EN54 defines performance requirements component by component. So EN54-2 is for control panels, EN54-7 for smoke detectors, EN54-23 for strobes. It ensures a baseline of global performance.
When approaching a new design, the sources stress that you have to start with occupancy classification and a rigorous risk assessment.
That risk assessment is the blueprint. The requirements for a theater are fundamentally different from a high-hazard storage facility. That assessment dictates the layout, the type of detection, and includes strict placement rules.
Like the 30-foot spacing for smoke detectors.
And placing them within 15 feet of any wall. And the wiring itself is also highly regulated.
Right. The National Electrical Code, NEC Article 760. It's not just about fire code, it's about electrical separation.
Exactly. It requires mandatory separation of the low-voltage fire alarm circuits from any line voltage circuits to prevent interference or faults from compromising the system.
And the system isn't legally usable until it passes the structured commissioning process. It's a three-stage workflow.
It is. It's the quality control gauntlet. You have pre-functional testing to check the basics wiring, power levels. Then functional testing, where you simulate alarms and confirm the correct outputs occur. And finally, acceptance testing, which is governed by NFPA 72, Chapter 14. This is the big one. It's a full demonstration of the system's performance to the authorities and the owners. It confirms everything works as programmed before the building can be legally occupied.
Once it's installed and certified, the challenge shifts to the long-term operational life cycle.
Yeah.
And our sources are heavy on this. Ongoing maintenance is not optional.
It's mandatory, and it's often the most overlooked part. Given that sensors get dirty, annual cleaning and sensitivity checks are necessary. If you skip this, you rapidly accelerate contamination drift, which leads to either sensor blindness or chronic false alarms.
And in this interconnected world, reliability also means digital security. We have to address the continuous need for firmware and configuration management.
This is a huge shift. Continuous vulnerability management is required, just like for any IT device. Manufacturers release software updates to patch bugs and security holes. And the system's configuration, all those cause and effect rules, must be meticulously managed and documented.
Let's directly address that analyst's concern. False alarm reduction. Chronic false alarms are more than just a nuisance. They create occupant complacency.
And you can't ignore the human psychology. If people hear the alarm weekly because of, say, burnt toast, they will hesitate during a real emergency. Reduction requires detailed analysis of what's causing the nuisance and then careful sensitivity calibration for that specific environment.
This brings us to the inevitable financial challenge. End-of-life planning. Components don't last forever.
And this is the hidden cost. Components degrade regardless of passing annual tests. The sources are clear. Sensors need to be replaced after 10 to 15 years based on manufacturer recommendations.
Even if they seem to be working.
Even if they pass the test. The internal components degrade, calibration drifts. Proactive planning for this replacement cycle is essential for long-term reliability.
And finally, what happens when the system must be temporarily disabled for maintenance or repairs? We have to discuss the impairment procedures.
NFPA 72 mandates a highly structured, documented impairment procedure. You have to notify the local fire department. And crucially, you have to implement compensating measures.
The most common being a fire watch.
A fire watch. A trained individual tasked with continuously monitoring the area and providing manual notification if there's a fire. The documentation tracks the exact duration of the impairment, which is vital for both regulatory review and liability protection.
We also briefly noted the specific zoning requirements that support the strategy of phased evacuation in high-rise buildings.
Right. Phased evacuation is an engineering strategy to prevent catastrophic congestion in stairwells. When a fire is detected, the system doesn't immediately notify the entire building. Instead, it might activate a full alarm on the fire floor, and the floors immediately above and below, but only a supervisory signal on the remaining floors. This enables a controlled, safe, sequenced evacuation, moving people out of immediate danger first.
We have dissected so many layers here, from the microscience of sensing chambers and low-frequency tones to the demands of physical redundancy and rigorous lifecycle management. The complexity is just astounding.
It is. And the synthesis of this deep dive, I think, confirms a critical lesson. Modern fire alarm systems are not just safety equipment. They are highly complex, multi-layered IT and operational technology networks governed by these incredibly rigid codes. Physical safety is entirely dependent on the integrity of that digital architecture, the topology, the redundancy, the programming, and that rigorous lifecycle management, including firmware updates and replacement schedules.
So system performance relies just as heavily on ongoing maintenance as it does on the initial design.
Absolutely.
And that reliance on integrated networks presents a profound and, frankly, a provocative final thought for you to consider as these systems become more and more connected.
Given the fire alarm system's deep and non-negotiable integration with building management systems controlling HVAC, elevators, security, the reliability and safety of a building's physical protection is now intrinsically linked to its overall cybersecurity posture. So you have to ask, if the fire panel or the broader BMS network it talks to has a vulnerability that gets exploited, what are the implications? What if a malicious actor remotely disables critical life-saving sequences like smoke control or the notification appliances? The convergence of physical safety and cyber risk is now total.
Thanks for listening. We will continue to talk about security and technology. See you in the next episode.